So we're going to look at some basic geometry problems, but we're going to think about how, well, if and how we can solve them exactly. And what I mean by that really is that we're getting rational answers so that we can write the answers as fractions. Because let's face it, wherever you stand on the view of the sort of validity of all of these irrational numbers, they're not on the same kind of epistemological level as fractions. You can't write them in reduced form, it's not clear how to add them. So for example, what's the square root of 2 plus pi? Maybe it has another sort of short expression, like a reduced form, like a fraction, but we don't know. So irrational numbers are basically not as nice, and so we're just going to restrict our attention to rational numbers. And this is basically what's done in physics. I mean, in computers and things, we represent things with integers, and really we're dealing with rational numbers when we're computing. So it seems sensible to do this. I mean, if we want to actually make a construction on a grid, we'd better have rational quantities so that we can express them exactly using the kind of geometry we can do. So, okay, in that case, we're only going to use rational numbers, and we're interested in the solution to this problem. So we have the unit circle, x squared, given by the equation x squared plus y squared is 1. That's a set of, well, that's these points which are a distance 1 from the centre of the circle. As well as that, we have the line given by the equation y equals a half. So if this line meets this circle, which it sure looks like it does, it'll meet it at the points x, y that satisfy both of these equations. So if we get this one and we substitute it into here, we can rearrange it to get this expression for x squared. So x squared is 1 minus a half squared. It's 3/4. So what's x? Well, there's going to be 2 points, one positive and one negative. At least this is the usual view. And those are given by the square root of this quantity, which is the square root of 3 divided by 2. And as I say, it can be plus or minus. Now the problem that sort of we have with this is that this is not a rational number. The square root of 3 is a very, very complicated thing, actually, which can't be written as a fraction, and it has a sort of decimal expansion that goes on forever and seems random, and we really don't understand it. So that this literally cannot be written as a fraction. Most people nowadays would say, well, this is a real number, but it's not a rational number. But let's take the viewpoint today that maybe this isn't even a number. Maybe this just isn't even a thing. It certainly isn't a thing that we can really point to in standard measurements. So I don't know, perhaps we could say that this line goes close to this circle but never goes through it. I mean, I'm not sure. How you want to interpret it is another question. For sure though, we're just restricting our attention to rationals. So this is not corresponding to rational points on the circle. That's coordinates x, y, which are rational numbers. A rational number, of course, is just something that you can write as one integer divided by another integer. Okay, so let's look at a slightly different problem now. Now we're going to have a look at the case where this line is not a half above the origin, this horizontal line. Now it's 4/5 above the origin. So it's the line y equals 4/5. Well, we can go through the same algebra as before. So we rearrange this thing in terms of x squared, and we find that x squared is equal to 9/25. Well, that works out very well, because that's equal to 3/5 squared. So x squared is 9/25. Well, then we can determine that x is just going to be the square root of that, which we can do, which is plus or minus 3/5. So this sort of answer is very different to the last one in the sense that it's rational. So this gives us some rational points on the circle which we can describe exactly. And why is this possible? Why does this work with 4/5 but it doesn't work with a half? Well, basically we can see that by substituting in these values of this value of x and this value of y into the unit circle formula, and we get this: 3/5 squared plus 4/5 squared is 1. Well, if you multiply both sides by 5, you'll see something that might be familiar to you. 3 squared plus 4 squared is 5 squared. This is what people call a Pythagorean triple. So this comes back to the sort of theorem of Pythagoras, which is that if you get the area of the squares on the two shorter sides of a right angle triangle and add them together, then you get the area given by the side of the longer triangle. And we can see it basically working here. So this is a sort of childish drawing of this 3, 4, 5 triangle. It goes 3 units across this way, it goes 4 units across this way, and 3 and 4 are such that if you like, the distance from this point here to this point here is given by 5 units up this way. So because 3, 4, 5 has this special relationship, we can do this geometry problem exactly. And so what we're interested in basically is finding more of these Pythagorean triples. Now this has been studied a lot. In fact, I think there was a very inspiring video by Wildberger recently on Babylonian tablets, where they basically had a table of these Pythagorean triples like thousands and thousands of years ago. They made this, and it basically corresponded to something like a trigonometry table, but it's exact in the sense that they're interested in dealing with, well, focusing on those geometry problems for which there are these exact rational answers. And yeah, I think that's an amazingly accurate way of doing it. Anyhow, what I'm going to do today is basically look at some generalizations of these Pythagorean triples to complex numbers. So basically I'll explain more later, but I'm going to be looking for complex integers that basically act like Pythagorean triples, in the sense that you can square one and then add another which is squared, and you get another complex integer which is squared. Now I'll define what that means later. Okay then, so let's now talk about complex numbers. So if you take your rational number system with sort of real rationals, so then you'd just be restricted to numbers that you can write as one integer divided by another. Well, if you then add in a new quantity, which we shall call I, and think of it as the square root of -1, so it has the property that I times I is -1. Well, basically, if you then look at the laws of arithmetic, you'll find that they're still valid, and that basically you have a sort of enlarged complex number system where we can think of the quantities as complex numbers which have a real part and an imaginary part. So a number can be expressed as something times the number 1, so something real times the number 1, plus something real times the number I, which is the square root of -1. And we can think of this geometrically as a point on the plane. So this sort of direction of the ordinary integers, 1, 2, 3, we can think of as right direction, and the direction of these imaginary integers, I, 2, I, 3, I, we can think of as perpendicular, going up. This gives the complex plane, also known as the Argand diagram. So a complex number like 1 plus 2i is a point that's 1 across and 2 up. Okay, so what about doing arithmetic on these things? What do we get if we take 1 plus 2i and we times it by itself? Let's have a look. Well, basically we just expand out the brackets just like usual and collect the terms together. We find that we've got 1 plus 4i plus 4i squared. What's I squared? Well, we know that I is square root of minus 1, so I squared is minus 1, so this would be 1 plus 4i take away 4, which is this. So what I'm eventually going to be getting around to is explaining how I got numbers like this, which are basically complex integers in the sense that they're a real integer plus an imaginary integer. So they're complex integers, but they satisfy Pythagoras's relationship. They're basically complex Pythagorean triples. So here we find that 1 minus 2i all squared plus 2 plus 2i all squared is 1 plus 2i all squared. And what I'm going to do today is go through a formula that I got which generated this complex Pythagorean triple and generates lots and lots of them. And I think probably the way to generate all of them is sort of understood in this method, and it can be at least partially derived geometrically, which is what I'm going to go through. So we're going to look at some circle geometry, and then we're going to think about how to generalize it to the complex plane. And there's some really interesting sort of unexplored things in this, I think. Okay, so let's have a look at how we can geometrically talk about these rational points upon a circle. So the normal way people sort of parameterize a circle, that is, describe a circle's points using numbers, is to use angles. But that can get problematic because you basically need a calculator to do trigonometry, and you can only do it approximately in the usual way. Sines and cosines are not easy to evaluate usually. But here's a completely rational approach. We can let t be any rational number, positive or negative, and then this formula here gives us a point upon this radius r circle centered on the origin. And so for any rational number t, this point, which has x coordinate r cubed minus rt squared, all divided by r squared plus t squared, and it has y coordinate 2r squared t divided by r squared plus t squared. This point is a point on this radius r circle, and moreover every rational point on this radius r circle can be written in this type of form. So basically this is a rational parameterization of the circle. So it's there's a sort of geometric reason behind this, which is okay. So let's see if we can get towards proving this. We're going to have a fixed point here at minus r0, and that's obviously going to be a point on the circle. And what we're going to do is we're going to draw a line through that point, and this line is going to go through this point, and it's also going to go through this point. So this is the point which is 0 across and t up. So then we can determine the equation for this line. So its gradient is going to be t divided by r, because if you go t up, when you get r across, you go t up. And we can see that if we had a line with a gradient, we have to shift it up by t in order to make it go through this point. So this line is given by the equation y equals t divided by r times x plus t. And the circle is given by the equation x squared plus y squared is r squared, excuse me. X squared plus y squared is r squared. So we have these two equations, and all we have to do is solve them to get this formula here. Okay, so let's now solve this algebraically. We know this is the equation for the line. Y is t over r times x plus t. And we know this is the equation for the circle. X squared plus y squared equals r squared. So we're going to be looking for rational x and y that satisfy both of these equations. The equation of the line and the circle. So here are our equations. I'm just going to go through this quickly because I guess you can pause the video if you want to go through the algebra. So there's the equation of the line. We'll times it by r to get this equation. ry equals tx plus tr. There's the equation for the circle. We'll substitute in, we'll times this by r squared. So we can write it as rx all squared plus ry all squared equals r to the power of 4. Now we see we've got an ry there, and we have an expression for ry here, so we'll substitute that in. We get this equation. R squared x squared plus, open bracket, tx plus tr, close bracket, squared equals r to the power of 4. And we can rearrange this into a quadratic equation in x, and we can solve it. Now, I mean, if you want to be rigorous, you should probably get the solution not by using the quadratic formula, because we don't want to be using square roots, but this is a sort of way to think of it. And so we have this quadratic formula giving us x, and what we have to do really is square root this quantity. So this is the quantity, open bracket, 2t squared r, close bracket, squared, take away 4, open bracket, r squared plus t squared, close bracket, times t squared r squared, take away r to the 4. So we want to be taking the square root of that quantity, but of course we're concerned with rational numbers, and we're concerned with when we can take the square root, and that ought to be indicated to us by the algebra. So let's have a look at the algebra of this expression for v and see if it is the kind of thing we can take the square root of without getting worrying about expressions and so forth. So here's our expression for v, and if we let capital R equal r squared and capital T equal t squared, that's just convenient notation, and if we just expand this out, we see it collapses down, and it can basically be written as 4 capital R cubed, or if you like, 2 times r to the power of 3 all squared. Well, that's great, because that's something all squared. Very easy to take the square root of that. We just rub out that 2 exponent there. So we go back to our equation for x, and we now know that the square root of t is 2r cubed. So this is our formula for x. Indeed, it is a rational thing, and basically, according to our quadratic formula, we're going to take plus or minus this 2r cubed. Now if we take minus it, we get the point where x equals minus r, and if we consult our original picture, see that's here, and the other point when we do plus the thing is this point here. Let's just check. Yeah, there it is. So when we do minus 2t squared r plus 2r cubed all over 2 times r squared plus t squared, that simplifies down to this, which is exactly the expression we want for x. Okay, so now let's finish our proof by finding out what y is. So we know x squared plus y squared is r squared. We can rearrange that to give y squared is equal to r squared minus x squared. We know we just had an expression for x squared. We can put that in. And if we write this as something all divided by r squared plus t squared all squared, we see that the numerator simplifies immensely, and we end up getting that y squared is equal to 4 times capital R squared times capital T all divided by capital R plus capital T all squared on the bottom. Capital R is little r squared, capital T is little t squared. So we can take the square root of this, and we find that y is equal to 2r squared times t divided by r squared plus t squared, just as we have it up here. So we've basically proved this formula now. Okay, so how are we now going to use this formula to get Pythagorean triples? Well, basically, we're just going to start by looking at a special case. So we're going to look at the case where the radius of a circle is 1. This is the standard sort of approach. So we're still in, this is still kind of a standard method to get these Pythagorean triples, and it's extremely beautiful, I think, because we use this lovely formula. We just evaluate it for the special case where the radius is 1, and we let t be a rational number, a divided by b. So a and b are integers here, b is not 0. And if we just plug in these numbers, we get this expression, which simplifies to b squared take away a squared divided by a squared plus b squared, comma 2ab divided by a squared plus b squared. So we get a really nice expression for these rational points of the circle. And you can already just plug in all the values of a and b here to generate, well, lots of values of a and b to generate lots and lots of rational points on the circle, and they are a very interesting structure. And I believe it's still kind of necessary to put more effort into understanding and visualizing this thing. For example, these rational numbers can be visualized in general as sort of members of this configuration of Ford circles, and so presumably these special rational numbers, which could be can be coordinates of points on a circle, ought to be a substructure of that. So there's possibly some fractal way of visualizing these things. Anyway, what we can do is multiply the xy that's on our circle. We can multiply it by a squared plus b squared. That's just going to be a number. And so we're basically multiplying out the downstairs of this, and we get that basically our coordinates xy times a squared plus b squared has a very simple form. The first coordinate is b squared minus a squared, and the second coordinate is 2ab. Now this is basically a formula giving you two sides of a Pythagorean triple. You can pick any integers, a and b, so b is not 0, and these will give you two sides of a Pythagorean triple. So in other words, you can draw a right angled triangle. You can have one side b squared minus a squared, the other side 2ab, those are the short sides, and then the long hypotenuse will have length a squared plus b squared, and whatever integers a and b you pick, this relationship holds. I mean, you can see this as a consequence of what we've already done, but I would recommend you just actually expand out this formula for yourself and see that the left hand side equals the right hand side. This is a Pythagorean triple. And in fact, all the Pythagorean triples have this sort of form. It's just that we can multiply them by integer constants to find others. So for example, you have a 3, 4, 5 triangle. Well, then there's also a 6, 8, 10 triangle just by multiplying the lengths by 2. But this formula gives you the less trivial ones. Here's one I quite like. If we set b as 4 and a as 3, well, we can work out these sides. So 2ab, that's 2 times 3 times 4, 24. And b squared minus a squared, that's 16 minus 9, which is 7. And you can check that 7 squared plus 24 squared is 25 squared, and a squared plus b squared is 25. That's 16 plus 9. So it all works out very nicely, and so let's think about how to generalize it. Okay, so we're going to now find some complex Pythagorean triples. I'm going to use Mathematica just because I don't want to make any mistakes on this sort of new calculation on this video, because this is all pretty new stuff. I'm doing my day job as a theoretical ecologist most of the time and don't get as much time for geometry as I wish these days. Anyway, take this formula that we derived, set the radius r equals to 1. That gives us this formula. So Mathematica uses curly brackets, but basically this is the x coordinate and this is the y coordinate of x and y on the unit circle. Now we're going to let t be a complex rational number. So a, b, c and d are integers, and t is equal to the rational number a divided by b plus square root of minus 1 times c divided by d. So if we substitute that value in of t in here, we get this thing here that we call v. So v has two components, v1 and v2. And these are basically points on the rational complex circle. Now let's multiply the entries of v by this number here. It's basically the denominator times b squared times d squared, and basically this still keeps the sort of Pythagorean aspect of this, but it turns it into a complex integer. So it has a form of an integer plus another integer times square root of minus 1. Mathematica uses I to denote square root of minus 1. So this number w here, so basically the thing about this is that these entries w1 and w2 are basically the short sides of a Pythagorean triple. So what's the hypotenuse length? Well, maybe length is a bad term since we're talking about complex numbers, but basically it's this denominator times b squared times d squared. It turns out if we treat that as a hypotenuse, so that'd be this form here, then this hypotenuse squared is equal to w1 squared plus w2 squared. So I just checked that calculation here. So basically this is sort of a formula. I mean the hypotenuse and yeah, I mean basically all of this stuff. I'll put a box around it. And this is basically a formula for a complex analogue of Pythagorean triples. So if we call these things A, capital A, capital B, and capital C, then yeah, we've got capital A squared plus capital B squared is capital C squared. Are these all the complex Pythagorean triples? I guess that if you get all of these and you consider all the numbers that you can get by multiplying them all by a given constant, so you can take any other complex integer k and you can times big A, big B and big C by k and you'll get another Pythagorean triple. And I guess you can get all of them in this kind of manner. And here's some visualizations of where these things are on the complex plane. And clearly there's still a lot of work to do. We need to understand this structure more, understand where the positions of these three points of these complex Pythagorean triples lie in the Argand diagram, and understand, more importantly, understand how the complex rationals can be visualized. I'm presuming there's some higher dimensional analog of Ford circles that I'm not aware of yet, and then presumably this kind of rational complex numbers that can be the coordinates of points on a unit circle can be viewed as some kind of interesting fractal substructure of that. So lots of things still to explore, I hope.